Okay. All right. So in this particular problem, you need to read it for yourself. And then I'm just going to give you the gist of it. You have two blocks. Block one moving to the right at 4 meters per second. Block two in blue moving to the left at negative 2.5 meters per second. Block two is attached to a spring. So when these two blocks collide, they will compress the spring. And we're asked to find these different parts. All right. So part A wants us to find the velocity of block two at the instant block one is moving at 3 meters per second. So once again, block one is initially moving to the right at 4 meters per second. Once it hits the spring, of course, it's going to slow down just a tad to 3 meters per second, and it wants us to find the velocity of block two when that happens. All right, so I'm just going to set up conservation linear momentum. Net momentum initially equals net momentum in the final frame. Initially, you have two objects moving, block one and block two. In this case, they're both moving. M1 V1I plus M2 V2I, and likewise on the right side, you have two blocks moving because it wants us to find the velocity of block two when V1F here is 3 meters per second. So it's dictating our conditions here for us. Okay, I'm just going to plug in values. M1 is 1.6. That's given in the statement. If you pause it and read the problem for yourself, V1I here is a positive 4 because it's moving to the right. We're going to add that to M2 being 2.1, which is also given. V2I is negative 2.5, so don't forget the fact that M2 here in this diagram is moving leftward, and the diagram is nice because it actually tells you that V2I here is negative 2.5, okay? Even if it doesn't give you the negative sign, you should definitely put a negative sign because this is a velocity, which is a vector, okay? All right, on the right side, likewise, M1 is given. V1F here is dictated for us. It wants us to find V2 when V1F is 3, M2 is 2.1, and then V2F is our only unknown. If you do the algebra stuff on the left side or calculator work here, 1.6 times 4 is 6.4, and then 2.1 times negative 2.5 will yield a negative value. And then 1.6 times 3 is 4.8, and then the term here 2.1 2VF hasn't done anything, so I just carry that down. So if you combine these terms here, 6.4 and negative 5.25, you get a positive 1.15 here. And then just move the 4.8 on the right side to the left to combine like terms. So if you do that, okay, you get negative 3.65, because don't forget, when you move stuff to the other side, it changes sign. And then from here, to find V2F, just divide both sides by 2.1, and then you have negative 3.65 divided by 2.1. You get a negative 1.74 meters per second. And so we can say that at the moment, block one slowed down to 3 meters per second. Block two, has always slowed down to negative 1.74 meters per second. So that is the answer to part A. Let's go ahead and do part B. Part B wants us to find the compression in the spring when block one's velocity is positive 3 meters per second. So just using common sense, these two blocks are going to collide, and because there's a spring in the center between them, it's going to compress the spring. How much? That's what we're asked to find here. So I'm just going to set up conservation mechanical energy. Here it says it's frictionless and all that good stuff, so it's a conservative system. MEI equals MEF. Initially, you have two terms moving, or you have two objects moving, M1 and M2, so you have two terms on the left side. And then on the right side, there are actually three terms, because at 3 meters per second for block one, block two is still moving at a rate of negative 1.74 that we just calculated in part A. However, there is another term here on the right side, and that is PE due to the spring, because now that the spring is compressed, there's energy stored in the spring, and that comes from the initial kinetic energy of the system. Okay, so don't forget about this PE spring, because it is being compressed. Because it's compressed, there's stored energy in the spring. All right, so I'm just going to go ahead and break up all this stuff. KI or KE1I is just 1/2 M1 V1I squared. KE2I is just 1/2 M2 V2I squared. Likewise on the right side, and then the function for PE spring is 1/2 KX squared, and this is from integrating Hooke's law. All right, other than that, values, I'm just going to let you do that. The only thing I do want to point out here is V2F. V2F is 1.74 because we calculated that in part A. Other than that, everything is pretty much given to you. Okay. Here, the spring constant is 600 newtons per meter. So if you read the problem, it says the spring constant has a value of 600 newtons per meter. So that's the only thing really different in this line. All right, so I'm just going to simplify my work. On the left side, you do your calculator work. The left term here reduces them about 12.8, and the second term here is about 6.5625. And then likewise with this term here is 7.2 and 1/2 times 2.1 times about 1.74 square is about 3.179, and then 1/2 times 600 is just 300. And then as you can see here, you have four coefficients without the variable x, 1, 2, 3, and 4. So I'm just going to go ahead and move the 7.2 to the left side. I'm going to move also the 3.179 to the left side to get x squared by itself. All right. So when you move it, change the sign. It goes from positive to negative, and then if you punch this in your calculator, you should get about 8.98. And then to get x squared by itself, divide both sides by 300. So 8.98 divided by 300 will give you about 0.02993. Okay, and I carry the decimal here quite a bit only because the value is small, so I don't want the answer to be too far off. Okay, now notice this is x squared, so we haven't gone x yet. So therefore, to get x by itself, we take the square root of both sides just to get rid of the exponent 2. So x is equal to the square root of this value, and then if you punch in your calculator, you should get about 0.173, and that is our answer for part B. Okay. All right, let's go ahead and do C, D, and E on the slide. Part C, kind of similar concept here as the other part. It wants us to find the velocity of block 1 at the instant block 2 is at rest. Okay, so how fast is block 1 moving when block 2 is at rest? So let's go ahead and crack it out. Set up conservation of momentum again. But you notice here on the right side, I want to cross out the second term. I'm crossing it out because it's telling us block 2 is at rest. Okay, so at some point when they collide, M2 is going to come to a stop while M1 is still moving. Okay, all right. So here, because I crossed that out, everything is pretty much given to me. On the left side, nothing has really changed because the initial momentum of the system is kind of given to us in this diagram. It gave you the mass of 2 blocks and the velocity of 2 blocks, so the initial momentum is given. Here on the right side, the only thing left really to find is V1F, because that's what it asks us to find, the velocity here of block 1. All right, so that's our only unknown. So clean up a little bit. Oh, excuse me. This should be, what is this? 6.4, not 6.5. Okay, I'm sorry, fat finger. Okay, once again, 1.6 times 4 is not 6.5, 6.4, whatever. Anyways, if you do that, you should get about 1.15 with the right value here. And then to get V1F by itself, you would just divide both sides by 1.6, and then that will give you a value of about 0.72 meters per second. And because it asks for velocity, make sure you include your directions in your statement. So I would say that the final velocity of block 1 when block 2 comes to a stop is positive 0.72 meters per second, or 0.72 meters per second eastward in this case, because the block is still moving to the right after block 2 has come to a stop. Okay, so that is your answer for part C. Okay, now part D wants us to find the compression once again when block 2 comes to a stop. So I'm just going to set up the same concept here. Mechanical energy is conserved, except I'm just going to go ahead and use a lot of information that I previously did in part B. So on the left side, nothing has changed. You still have initially 2 objects moving. Okay. On the right side, though, you notice here, even though I wrote it out, I went ahead and crossed out KE2F because block 2 will momentarily come to a stop, because that's what it says. And then PE spring, though, is still there because it's still being compressed, right? The spring is still being compressed. All right. Other than that, I'm just going to go ahead and plug and chug. Here, I'm just going to reduce that to that, and then KEI, and then KE1I and KE2I, which has been calculated in the previous part. So these numbers come from the early part of the video. So if you need to pause and go back, and then KE1F here is just 1/2 M1 V1F squared. So the 0.72 is right here in part C. Okay, so part C, we're asked to find the velocity of block 1 when block 2 comes to a stop, which we found to be 0.72. So I highlight the 0.72 there just to show you where that value comes from. And then PE spring reduces down to just 300x squared, because the 1/2 times 600 is just 300. All right, so if you simplify this, the left side comes out to be about 19.3625, and then the 1/2 times 1.6 times 0.72 square here comes out to be about 0.415, and then to get 300x squared by itself, subtract this value from both sides. So 19.3625 minus 0.415 there, and then at the same time, to get x squared by itself, again, we did this in the previous step or previous parts, divide both sides by 300. So if you take the difference here and then divide it by 300 just to get x squared by itself, you get about 0.0632, and then to square root that, and then we're just done. Okay, so the answer for part D is about 0.25 meters, and that's that. Now part E though asks you, is it possible for both blocks to come to rest while the spring is being compressed? And then the answer I came up with is that it's no. Okay, because if both blocks came to a stop, then that would imply that the momentum is zero, because the momentum of the system is mass times velocity. Well, if both blocks comes to a stop, the velocity of both blocks would be zero, which would suggest that the final momentum is zero. But that cannot be, because momentum has to be conserved here in an isolated system. So we found earlier that the initial momentum of the system is 1.15. Watch where I'm circling, right? All these values on the left side reduces down to just about 1.15. So if the initial momentum of the system is 1.15, it has to remain that way. It cannot be zero, because if it is zero, then the law of conservation of momentum is violated. So here we go. So once again, the answer for part E is no, because if both blocks came to a stop, the final momentum of the system would be zero, which it cannot be, because the initial momentum of the system is 1.15 and it has to remain that value throughout collisions. Okay? All right. Stay nerdy. Don't be whack.